The star is already moving toward us. Right now, at this very moment, while you draw breath and listen to these words, a dim orange sun is hurtling through the galaxy at more than 50,000 kilometers per hour, aimed almost directly at our cosmic address. It has been falling toward us for millions of years. It will continue falling toward us for over 1 million more, and when it finally arrives, sometime around the year 1290,000 AD, it will pass closer to our Sun than any known star has approached in the entire recorded history of the cosmos. Closer than anything will approach again for tens of millions of years afterward. Its name is Gliese 710, and most people have never heard of it. This is not the death of the solar system. This is not an impact. This is not even, strictly speaking, a collision at all. At its closest point, Gliese 710 will still be more than 10,000 times farther from our Sun than the Earth is, a distance so vast that if you could somehow stand on a planet orbiting that dim orange dwarf at the moment of closest approach, our Sun would appear as nothing more than an extraordinarily bright star in the night sky, casting no warmth, offering no comfort, just another distant point of ancient light among billions. And yet what happens during that passage, what has already been set into motion by the gravitational mathematics of stellar trajectories, may ripple through our solar system for millions of years afterward. The star will pass. The star will continue on its journey through the galaxy, growing smaller and dimmer in our sky until it vanishes entirely into the cosmic background. But in its wake, it may leave something behind, a disturbance, a tremor, a subtle gravitational whisper that travels through the frozen darkness at the very edge of everything we call home. To understand why this matters, we need to travel outward. We need to leave behind the warm stone and blue water of Earth, leave behind the familiar rust-coloured deserts of Mars, the banded storms of Jupiter, the delicate rings of Saturn. We need to pass beyond the ice giants, beyond the scattered disk of frozen worlds that includes Pluto and its distant cousins, beyond even the heliopause where the solar wind finally gives way to the interstellar medium. We need to travel so far from the Sun that its light takes more than a year to reach us, and then we need to keep going. Out there, in a region of space so dark and so cold that the temperature hovers barely above absolute zero, there exists a vast shell of frozen material that has never been directly observed by any human instrument. We know it must be there, the mathematics demands it. The comets that occasionally fall screaming into the inner solar system, trailing tails of sublimating ice millions of kilometers long, must come from somewhere. And the orbits of those long-period comets, the ones that take thousands or even millions of years to complete a single journey around the Sun, point back to a common origin, a reservoir of primordial ice and rock that surrounds our star like a hollow sphere of forgotten creation. This is the Oort Cloud. Picture it, if you can. Picture the Sun reduced to a bright star, brighter than any other star in the sky, but still just a point of light, still too distant to warm anything. Picture yourself suspended in that darkness, surrounded on all sides by frozen objects, chunks of ice and rock and organic compounds that have been drifting in this void since before the Earth existed, since before the Sun itself ignited, since the very earliest moments when the primordial solar nebula was still collapsing under its own gravity. These objects are not packed together. This is not a dense field of debris like the asteroid belt depicted in science fiction. The Oort Cloud is so vast, so unimaginably enormous, that the typical distance between any two of its frozen inhabitants is greater than the distance from the Earth to the Sun. If you were somehow transported to the middle of this cloud, you would see nothing. Absolute darkness in every direction. The nearest chunk of primordial ice might be 1 billion kilometers away, invisible, silent, drifting on an orbit so vast that it has completed perhaps a single revolution around the Sun since the dinosaurs walked the Earth. And yet, there are trillions of them, perhaps hundreds of trillions. Some astronomers estimate that the total mass of the Oort Cloud might exceed the mass of all the planets combined, though spread so thin, so diffuse across such an incomprehensible volume of space, that it would take tens of thousands of years of travel at the speed of our fastest spacecraft to cross from one edge to the other. This is the realm that Gliese 710 will disturb. The star itself is unremarkable as stars go. It is what astronomers call a K-type main sequence star, sometimes more poetically described as an orange dwarf. It burns cooler and dimmer than our Sun, putting out only about half the luminosity, glowing with a warm amber hue that would seem almost cozy if you could somehow get close enough to feel its radiance. It has about 60% of our Sun's mass, which means it will live far longer than our star. Orange dwarfs can burn steadily for tens of billions of years, outlasting the Sun by epochs, continuing to shine long after our own star has swelled into a red giant and shed its outer layers into a planetary nebula. Right now, Gliese 710 sits about 62 light-years from Earth, an unremarkable distance for a star in our galactic neighbourhood. If you went outside on a clear night and knew exactly where to look, you could find it with a good pair of binoculars in the constellation Serpens, though it would appear as nothing special, just another dim point among the thousands visible to the aided eye. It is number 710 in a catalogue of nearby stars compiled by the German astronomer Wilhelm Gliese in the 1950s and updated several times since, a designation that gives no hint of the star's extraordinary future. But the European Space Agency's Gaia spacecraft changed everything. Launched in 2013, Gaia has spent the past decade measuring the positions and motions of nearly 2 billion stars with a precision that would have seemed like magic to astronomers of previous generations. It doesn't just tell us where stars are, it tells us where they're going. By measuring the incredibly tiny shifts in a star's apparent position over time, combined with spectroscopic measurements of how fast each star is approaching or receding from us, Gaia can project stellar trajectories millions of years into the future, and when astronomers applied those calculations to Gliese 710, the results were startling. The star is not just moving in our general direction, it is aimed almost precisely at us, approaching at a rate that means it covers roughly the distance from the Earth to the Sun every 7 years. Decade after decade, century after century, millennium after millennium, it draws closer. The motion is imperceptible on human timescales. You cannot watch a star approach across interstellar distances the way you might watch a car drive toward you on a highway. But the mathematics is certain, the trajectory is clear, and the destination is the inner reaches of the Oort Cloud itself. Earlier estimates, made before Gaia's precise measurements were available, suggested that Gliese 710 would pass within about 1.5 light-years of the Sun, a close approach by stellar standards, but not exceptionally so. Many stars have passed within similar distances over the Sun's 4.6 billion-year history, but Gaia's data refined the prediction dramatically. The new calculations, published in 2016 and confirmed by subsequent observations, show that the star will pass within approximately 10,000 astronomical units of the Sun. 1 astronomical unit is the distance from the Earth to the Sun, about 150 million kilometers. 10,000 astronomical units is still an enormous distance, roughly a sixth of a light-year, or about 1.5 trillion kilometers. But in terms of stellar approaches, it represents something extraordinary. This is close enough that Gliese 710 will pass through the inner regions of the Oort Cloud itself, threading through the densest concentration of those ancient frozen bodies, disturbing orbits that have remained stable since the formation of the solar system. The probability calculations have been run again and again. Different research teams using different methods and slightly different data have all converged on the same conclusion. There is a greater than 90% chance that the closest approach will fall somewhere between 9,000 and 13,500 astronomical units. There is even a small but non-zero probability, perhaps 1 in 10,000, that the star could pass as close as 2,000 astronomical units, well within what astronomers consider the inner Oort Cloud, a region that might contain a higher density of primordial material than the outer reaches. This is not speculation. This is not science fiction. This is orbital mechanics, the same mathematics that allows us to land spacecraft on comets and thread probes through the narrow gaps in Saturn's rings. The star is coming. The question is not whether it will arrive, but what will happen when it does. To understand the answer, we need to think about gravity in a different way than we usually do. We tend to imagine gravity as a force of immediate drama, the apple falling from the tree, the moon being held in orbit, the black hole tearing apart anything that ventures too close. But gravity also works on timescales so vast that human consciousness struggles to comprehend them. The gravitational pull of a distant mass can be almost infinitesimally small, so weak that no instrument could detect it, and yet over millions of years that tiny persistent tug can fundamentally alter the trajectory of an orbiting body. Consider a chunk of ice in the outer Oort Cloud, a primordial remnant the size of a small mountain, tumbling slowly through the darkness on an orbit that takes it 70,000 years to complete a single journey around the Sun. For most of those 70,000 years, it feels almost nothing, just the faint gravitational whisper of our distant star, so weak at that distance that it would take centuries for its effect to become measurable. The orbit is stable. It has been stable for billions of years. Nothing disturbs it. Nothing changes. Then Gliese 710 arrives. The star passes through the region over the course of several thousand years, moving at its steady pace, its gravity reaching out in all directions like an invisible hand sweeping through a cloud of dust. For most Oort Cloud objects, the effect is minimal, a slight perturbation, a minor adjustment to their enormous orbits, nothing dramatic. But for some objects, the ones that happen to be positioned just right, the ones whose orbits bring them close enough to the passing star at the critical moment, the effect can be profound. Gravity doesn't simply pull objects directly toward the massive body exerting the force. It changes their orbits, it adds energy or removes it, depending on the geometry of the encounter. A frozen body that has been circling the Sun in a nearly circular orbit for 4 billion years might suddenly find itself on a highly elliptical path, one that plunges inward toward the distant point of light that it has orbited for so long. This is how comets are born. Not created, the material has existed since the formation of the solar system, but transformed from distant frozen wanderers, invisible and inert, into falling bodies on trajectories that will eventually carry them into the inner solar system, where the Sun's heat will sublimate their ices and create the spectacular tales that have terrified and awed humanity since before recorded history. The process takes time. An object disturbed by Gliese 710's passage in the year 129 million AD might not reach the inner solar system for another million years, or 2 million, or 5 million. The Oort Cloud is so distant, and orbital periods there are so long, that the consequences of the stellar passage will unfold across geological timescales. The star will come and go, growing from a dim point to a bright orange light to a dim point again and finally vanishing, long before the first wave of disturbed comets begins to fall inward. This is why the passage of Gliese 710, despite being the closest known stellar approach in the past or future history of the solar system, poses no immediate threat to Earth. No direct threat at all, really, to the humans alive today or to hundreds of thousands of future generations. The star itself will never come close enough to affect anything in the inner solar system directly. Its gravity will be far too weak at closest approach to disturb the orbit of any planet, any asteroid in the belt, any moon of any world we have explored. But the Oort Cloud is a different matter. Simulations run by astronomers at institutions around the world have attempted to quantify what Gliese 710's passage might do to that frozen shell of primordial material. The results vary depending on the assumptions made about the Oort Cloud's density, distribution, and extent, all of which remain poorly constrained by direct observation. But the consensus suggests that the stellar passage will significantly increase the flux of long-period comets entering the inner solar system for millions of years afterward. Some models predict a doubling of the comet rate. Others suggest increases of tenfold or more. The uncertainty is enormous, reflecting how little we truly know about the Oort Cloud structure. But the direction of the effect is not in doubt. More comets will fall inward after Gliese 710 passes than were falling before. The frozen depths of the outer solar system will be stirred, and some of that stirred material will eventually find its way sunward. How many of those comets might strike the Earth? This is where the mathematics becomes both reassuring and humbling. The inner solar system is vast and mostly empty. Even with a significantly elevated comet flux, the probability of any individual comet striking our planet remains extremely small. Comets are relatively small objects, typically a few kilometers across at most, moving through a volume of space that dwarfs them beyond comprehension. The Earth is a tiny target, a pale blue speck in an ocean of emptiness. And yet 66 million years ago, an object roughly 10 kilometers across, probably an asteroid rather than a comet, but the distinction matters little to the creatures that lived through the impact, struck what is now the Yucatan Peninsula and ended the age of dinosaurs. The non-avian dinosaurs had ruled the Earth for more than 160 million years. In a geological instant they were gone, along with roughly 3/4 of all species then living. Life recovered, eventually. but the impact reset the evolutionary clock in ways that shape the world we know today. Comets have struck the Earth before. They will strike again. The question is not if, but when, and the passage of Gliese 710 will shift those probabilities, however slightly, for millions of years to come. But we're getting ahead of ourselves. The star is still 62 light-years away, and the story of its approach, and what it means for our understanding of the cosmos, requires us to consider questions that reach far beyond the immediate threat calculus of impact probabilities. Consider what it means that we know this at all. For all of human history prior to the space age, the stars were fixed. This was the fundamental assumption of practical astronomy, the stable backdrop against which the planets wandered and the moon traced its monthly path. Ancient astronomers could predict eclipses centuries in advance because they understood the mechanics of the solar system, but the stars themselves were points of light whose positions changed imperceptibly over human lifetimes. The notion that stars might be moving toward or away from us, that they might have destinations and trajectories and cosmic appointments scheduled millions of years in the future, would have seemed absurd. It was only in 1718 that the English astronomer Edmund Halley, the same Halley whose name would be given to the famous comet, noticed that 3 bright stars, Sirius, Arcturus, and Aldebaran, had shifted from the positions recorded by ancient Greek astronomers. The motion was tiny, detectable only because the Greeks had left reasonably precise observations, and nearly 2,000 years had elapsed. But it was real. The stars were moving. This discovery shattered one of the oldest assumptions about the nature of the universe. If the stars moved, then their current arrangement was temporary, a snapshot of a moment in cosmic time. The constellations familiar to human eyes, Orion, the Big Dipper, the Southern Cross, were not eternal fixtures but transient patterns that would slowly distort and eventually become unrecognizable over hundreds of thousands of years. And if the stars moved, then sometimes they must pass close to one another. In a galaxy containing hundreds of billions of stars all orbiting the galactic center, on complex interweaving paths, close approaches must be common on astronomical timescales. Our Sun has almost certainly had numerous stellar visitors over its 4.6 billion year lifetime, stars that passed within a light year or two and moved on, leaving no record that human scientists could detect. But Gliese 710 is different. Gliese 710 is the first stellar approach that we have seen coming with enough advance warning and enough precision to study in detail. We can predict not just that it will come close, but how close. We can model what its gravity will do to the Oort Cloud before the event actually happens. We can trace the star's current trajectory backward in time and forward into the deep future, reconstructing its journey through the galaxy over millions of years. This is, in a sense, a kind of cosmic weather forecasting. We cannot change what is coming. We cannot divert a star the way we might someday learn to divert an asteroid. The energies involved are too vast, the distance is too great, the timescales too long for any conceivable technology to affect them. But we can watch, we can predict, we can understand, and perhaps most importantly we can recognize our place in this cosmic choreography. The solar system is not static. It never has been. The planets we see today, orbiting in their stable configurations, are the survivors of a chaotic early period when gravitational interactions sent some primordial bodies spiraling into the Sun and others careening outward into the frozen depths. The asteroid belt is the remnant of a planet that never formed, its growth stunted by Jupiter's overwhelming gravity. The Oort Cloud itself is debris, material that was scattered outward by the giant planets during the solar system's first few 100 million years and has been drifting in the cold ever since. Into this already complex system, the galaxy occasionally sends visitors, stars passing nearby, interstellar objects like Oumuamua and Comet Borisov, both discovered in recent years, tumbling through on hyperbolic trajectories that will carry them back out into the void. The Sun and its family of planets are not isolated. They are embedded in a larger cosmic environment, subject to forces and influences that operate on timescales our brief lives can barely comprehend. Gliese 710 is simply the next visitor we know about. The most significant one, yes, in terms of how close it will come, but not the only one. Gaia's data has revealed numerous other stars that will make relatively close approaches over the coming millions of years, though none as close as Gliese 710, and none with the same potential to disturb the Oort Cloud. The star itself continues on its way. utterly indifferent to the calculations of astronomers on a small rocky world it has never seen. It has been travelling for millions of years already, moving through the galaxy on an orbit of its own, occasionally passing close to other stars that may have harboured their own observers, wondering at the approaching orange light. In another million years it will reach our vicinity, sweep through the outer reaches of the solar system's influence, and continue on, growing dimmer in our sky until it vanishes among the billions of background stars once more. What will Earth be like when it arrives? What will humanity be like, if humanity still exists in any recognisable form? These are questions that the mathematics of orbital mechanics cannot answer. The precision that allows us to predict Gliese 7.10's trajectory to within a few hundred astronomical units breaks down completely when applied to human civilization. We cannot know what technologies our descendants will possess, what forms their societies will take, whether they will have spread to other worlds, or retreated to a diminished existence on a ravaged Earth, or transcended biological existence entirely in ways we cannot imagine. What we know is that the star is coming. We know approximately when it will arrive. We know, within reasonable uncertainties, how close it will pass and what effects its gravity may have on the frozen material at the edge of our solar system. And we know that those effects, whatever they turn out to be, will unfold across timescales so vast that even the eventual arrival of disturbed comets in the inner solar system will be separated from the star's passage by millions of additional years. This is cosmic time. This is the rhythm of the universe, playing out in movements so slow that generations upon generations of human lives pass in what amounts to a single heartbeat. The star approaches. The comets wait in their frozen darkness. And we, the observers, have been given the remarkable gift of knowing that it is all happening, of being able to look up at the night sky and point toward the constellation Serpens and say, with scientific certainty, there is something coming. Whether that knowledge is a warning, a wonder, or simply an interesting fact about an indifferent cosmos is a question each of us must answer for ourselves. The story of Gliese 7.10 is ultimately a story about time, about the vast gulfs of it that separate cosmic events from their consequences, about the brief window of awareness that human civilization has opened onto an ancient and ongoing process, about the peculiar position we occupy as creatures who can comprehend timescales we can never experience. But it is also a story about the structure of the solar system itself, about the frozen wilderness beyond the planets, about the remnants of creation that have been circling in darkness since before life began on Earth. To understand what Gliese 7.10 will do, we need to understand the Oort Cloud, not just as an abstraction, not just as a mathematical necessity, but as a real place, a vast sphere of ancient material that extends trillions of kilometers in every direction, containing more frozen water than exists in all the oceans of Earth combined. And that understanding begins not with telescopes or spacecraft, but with falling ice, with the comets that have been plummeting into the inner solar system since the earliest days of human awareness, trailing fire across the sky, terrifying and mystifying our ancestors, and ultimately revealing to modern astronomers the existence of a reservoir of primordial material that we can barely begin to imagine. The Great Comet of 1811 was visible to the naked eye for more than 260 days, the longest recorded cometary observation until modern times. For 9 months, it hung in the sky like a celestial sword, its tail stretching across dozens of degrees, bright enough to cast shadows on moonless nights. Armies marched beneath it. Farmers planted and harvested and planted again while it watched. Napoleon, preparing his disastrous invasion of Russia, reportedly took it as an omen of his coming triumph, a mistake that would cost 500,000 lives. But the comet itself was simply falling. It had been falling for millions of years, descending from the unimaginable cold of the outer solar system on an orbit that stretched so far that astronomers of the time struggled to calculate its parameters. It rounded the sun in September of that year, achieving its moment of maximum brightness, and then continued outward again, climbing back toward the frozen depths from which it had come. Its orbital period is estimated at roughly 3,000 years. It will not return until sometime around the year 4800 AD, assuming its orbit remains stable and nothing disturbs it during its long exile in the outer darkness. When it does return, what civilization will watch it fall? What eyes will turn upward to see the ice sublimating in the sun's heat, the tail streaming outward under the pressure of solar radiation, the ancient material of creation becoming briefly, spectacularly visible before retreating once more into the void. These are the visitors from the Oort Cloud, the messengers from a realm we cannot see directly, the evidence that something exists out there in the darkness beyond the planets, and it is this realm, this frozen sphere of primordial material, that Gliese 710 will disturb. The consequences will take millions of years to unfold fully, but the cause is already in motion. The star approaches, and on some future night, in some unimaginably distant era, a new comet may appear in the sky of whatever world we inhabit then, falling inward on an orbit that began to change in the year we number as 190,000 AD. That comet's fall will be Gliese 710's legacy, a gentle ripple spreading through time from the moment of closest approach, a gravitational echo that outlasts the star's passage by epochs. And it all begins with a dim orange light, 62 light-years away, growing slowly brighter. The Oort Cloud has never been photographed. No spacecraft has visited it. No telescope has resolved a single one of its countless billions of icy bodies drifting in the perpetual night beyond Neptune's orbit. Everything we know about this vast spherical shell of frozen debris comes from inference, from mathematics, from the patient tracking of comets as they fall screaming into the inner solar system and then climb back out toward the dark. And yet we know it exists with the same certainty that we know about atoms or black holes or the molten iron churning at the centre of Earth, because the evidence is overwhelming, because the mathematics demands it, because no other explanation fits the observed behaviour of the long-period comets that occasionally grace our skies. The story of the Oort Cloud's discovery is, in a sense, the story of a man staring at orbital mechanics and refusing to accept the obvious conclusion until a better one presented itself. In 1950, the Dutch astronomer Jan Hendrik Oort was puzzling over a problem that had nagged at comet specialists for decades. Long-period comets, those with orbital periods measured in thousands or even millions of years, appeared to fall into the inner solar system from all directions, not from a single plane like the planets or the asteroids or the short-period comets that hug the ecliptic, from everywhere, from above the plane of the solar system and below it, from every conceivable angle, as if they were being dropped toward the sun from a spherical shell surrounding the entire planetary system. Some of these comets had orbits so elongated, so extreme, that their farthest points from the sun, their aphelia, lay tens of thousands of astronomical units away. 1 astronomical unit is the distance from Earth to the sun, roughly 150 million kilometres. 10,000 astronomical units is 150 trillion kilometres. 20,000 astronomical units approaches a quarter of a light year. These comets were travelling from distances that seemed almost absurd, from regions so remote that the sun would appear as merely the brightest star in the sky, its gravitational grip so tenuous that a passing breath of wind, were there any wind in that void, might tear a comet free entirely. Oort recognised that these extreme orbits posed a problem. Comets lose material every time they pass through the inner solar system. The sun's heat sublimates their ices, blasting gas and dust into space, creating the spectacular tails that make comets so beautiful and so temporary. A comet on a short-period orbit, passing close to the sun every few decades, will eventually exhaust itself, becoming a dead husk of rock and carbon, indistinguishable from any small asteroid. Even a long-period comet returning to the sun every few thousand years cannot survive forever. After a few hundred passes, it will have boiled away its volatile materials entirely, and yet long-period comets keep appearing. Every year, on average, 1 or 2 new long-period comets are discovered, making their first observed approach to the sun, falling inward from the darkness as if freshly released from some cosmic freezer. This meant that the source region had to be vast enough to contain an essentially inexhaustible supply of cometary nuclei, vast enough that the loss of a few comets every year to the inner solar system would not noticeably deplete the reservoir over billions of years. Oort calculated that this source region must contain at least 100 billion comets, perhaps several trillion. He calculated that it must extend from roughly 2,000 astronomical units from the Sun out to perhaps 50,000 or even 100,000 astronomical units, a shell of frozen debris half a light-year thick, surrounding the Sun in all directions, containing the frozen remnants of the solar nebula from which the planets themselves had formed. He called it the cometary cloud. Others would call it the Oort Cloud, and the name would stick, a lasting monument to the man who had looked at falling ice and deduced the existence of a vast frozen wilderness that no human eye would ever see directly. Understanding the structure of the Oort Cloud requires grasping scales that the human mind was never evolved to comprehend. We are creatures of the savannah, designed by natural selection to track the movements of prey animals across distances of a few kilometres, to estimate the height of trees we might climb, to judge whether a river is too wide to cross. The distances between stars are not merely large in the way that mountains are large or oceans are wide. They are large in a way that represents a fundamental break from all human experience, a category of vastness that our intuition simply cannot process. The nearest star to the Sun is Proxima Centauri, at a distance of approximately 4 light-years. Light itself, travelling at 300,000 kilometers per second, takes 4 years to cross that gap. A spacecraft travelling at the speed of the Voyager probes, roughly 17 kilometers per second, among the fastest objects ever launched by humanity, would take over 70,000 years to reach Proxima Centauri. The Oort Cloud extends roughly a quarter of that distance, reaching perhaps a light-year from the Sun before the gravitational influence of the galaxy itself begins to dominate over the Sun's pull. This means the Oort Cloud is not some tiny shell hugging the outer reaches of the planetary system. It is, in terms of volume, the solar system. The planets, the asteroids, the Kuiper belt, everything we think of when we imagine our cosmic neighbourhood. All of that is a tiny bright core at the centre of a vast dark halo of frozen debris that extends outward for trillions upon trillions of kilometres. The comets in the outer Oort Cloud move so slowly that time itself seems to freeze. At 100,000 astronomical units from the Sun, the orbital period of a comet is measured in millions of years. A comet at that distance, if it could somehow be observed, would appear almost stationary against the background stars, drifting imperceptibly along an orbit so vast that 1,000,000 years might pass between observable changes in its position. These are the true ancients of the solar system, objects that have been circling in the darkness since the Sun was young, since the planets were still accreting from the disk of gas and dust that surrounded the newborn star. They have never been heated, never been altered, never experienced anything but the faint glow of distant starlight and the occasional gravitational tug of a passing star. They are time capsules from the formation of the solar system, preserved in the deepest freeze the universe can offer, waiting for something to nudge them out of their stable orbits and send them falling inward toward the distant fire of the Sun. And this is where Gliese 710 enters the story, not as a destroyer, not as a harbinger of immediate doom, but as a gentle hand reaching into that frozen reservoir and stirring it ever so slightly. The physics of what will happen when Gliese 710 passes within 10,000 astronomical units of the Sun is well understood, even if the specific consequences cannot be predicted. When a massive object passes near a smaller one, it transfers momentum through gravity. This is the same principle that allows spacecraft to perform gravity assists, slingshotting around planets to gain speed. It is the same principle that allows binary stars to exchange energy over millions of years. And it is the same principle that will allow Gliese 710 to perturb the orbits of countless Oort Cloud comets during its passage through our cosmic neighbourhood. The key variable is the distance of closest approach, which astronomers call the perihelion when discussing objects in the solar system. Gliese 710 will pass at approximately 10,000 astronomical units from the Sun, which sounds like an enormous distance, and it is by human standards. It is roughly 10 times the distance to the outer edge of the Kuiper belt, roughly 50 times the distance to Neptune. But by the standards of the Oort Cloud, it is disturbingly close. The inner Oort Cloud, sometimes called the Hills Cloud, after the astronomer Jack Hills, who first proposed its existence, extends from roughly 2,000 to roughly 20,000 astronomical units from the Sun. The outer Oort Cloud extends from there out to perhaps 100,000 astronomical units. This means Gliese 710 will pass directly through the inner Oort Cloud, cutting through the densest region of cometary material like a ship passing through a harbour full of small boats. Every comet within a few thousand astronomical units of the star's path will have its orbit altered. Some will be accelerated slightly, their orbits widening. Others will be decelerated, their orbits tightening, their perihelion distances shrinking. And a few, the unlucky ones, or perhaps the lucky ones depending on your perspective, will have their orbits altered so dramatically that they will begin falling toward the inner solar system, beginning journeys that will take millions of years to complete. The mathematics of gravitational perturbation is elegant in its simplicity and terrifying in its implications. The effect of Gliese 710's passage on any individual comet depends on the distance between the star and the comet at closest approach, the relative velocity of the encounter, and the mass of the star. Gliese 710 is roughly 60% as massive as the Sun, making it a substantial gravitational influence. Its velocity relative to the solar system is modest, perhaps 10 to 15 kilometers per second at perihelion, which means it will linger in the Oort Cloud region for a considerable period of time, maximizing its gravitational effect. Astronomers have calculated that the star will spend roughly 100,000 years within 10,000 astronomical units of the Sun, a geological eye blink but an eternity by the standards of orbital mechanics. During that time, it will exert continuous gravitational influence on billions of cometary bodies, nudging them out of the stable orbits they have occupied since the solar system's formation. The term astronomers use for this process is comet shower. It is a gentle phrase for what is, in cosmic terms, a significant restructuring of the outer solar system's dynamics. When Gliese 710 passes, it will trigger a comet shower, a sustained increase in the rate at which long-period comets fall into the inner solar system, not immediately, of course. The comets disturbed by Gliese 710's passage in the year 129 million AD will take millions of additional years to complete their journeys inward. The first of these disturbed comets might not reach the inner solar system until the year 3 million AD or later. The peak of the comet shower, the period of maximum bombardment, might not occur until 5 or 6 million years after the star's passage, and the shower itself will persist for tens of millions of years, a slow rain of ancient ice falling from the darkness, a legacy of a gravitational encounter that will have ended eons before the first disturbed comet streaks across the sky of whatever world watches it fall. This is the timescale on which the universe operates, the pace at which cosmic events unfold. A star passes, comets are disturbed, millions of years pass, the comets arrive, more millions of years pass, the shower fades, and the solar system continues on, slightly altered, carrying within it the gravitational memory of an encounter that no human will ever witness directly. We are creatures who measure our lives in decades, our civilizations in millennia, our species' existence in hundreds of thousands of years at most. The comet shower triggered by Gliese 710 will outlast any reasonable projection of human survival by a factor of 1,000. It is an event that belongs not to us, but to whatever inherits the solar system after we are gone, and yet we can calculate it. We can model it. We can predict with reasonable accuracy how many comets will be disturbed, how their orbits will change, how long the shower will last. This is perhaps the most remarkable aspect of the entire story. Not that a star will pass near the Sun, not that comets will be disturbed, but that a species of large-brained primates on a small rocky planet has developed the mathematical tools necessary to predict events that will occur 1 million years in the future. We cannot know what the weather will be next month with any certainty. We cannot predict the movements of stock markets or the outcomes of elections or the behavior of individual human beings. But we can tell you with considerable confidence that in the year 1890,000 AD, a small orange star will pass within 10,000 astronomical units of the Sun and trigger a gravitational disturbance in the Oort Cloud that will send comets falling into the inner solar system for the next 50 million years. The contrast between our uncertainty about the near future and our clarity about the distant future is one of the strangest features of modern physics. We understand gravity better than we understand ourselves. The specific effects of Gliese 710's passage have been modelled extensively by astronomers around the world. The most detailed simulations suggest that the star will increase the flux of long-period comets entering the inner solar system by a factor of roughly 10 compared to the current baseline rate. This sounds alarming until you remember that the current rate is extremely low, perhaps 1 or 2 potentially hazardous long-period comets per century. A tenfold increase means perhaps 10 or 20 such comets per century, spread over tens of millions of years. This is not a civilization-ending catastrophe. It is not even, in any meaningful sense, a crisis. It is a statistical increase in an already rare phenomenon, a slight uptick in cosmic rainfall that that will be utterly imperceptible to any observer without access to extremely precise records kept over extremely long time periods. But within that statistical increase lies a genuine danger, a real possibility that must be acknowledged even as we recognise its low probability. Every comet that enters the inner solar system is a potential impactor. Every comet that passes near Earth's orbit is a potential extinction-level event. The dinosaurs were not killed by an asteroid that was certain to hit Earth. They were killed by an asteroid whose probability of hitting Earth was indistinguishable from zero until the moment of impact. The universe does not care about probabilities, it cares about outcomes, and the outcome of a major cometary impact is so severe, so utterly catastrophic for any biosphere unlucky enough to be in the way, that even a small increase in the probability demands attention. The energy released by a cometary impact is difficult to conceptualize. Comets are relatively small objects, typically a few kilometers across at most, composed of ice and rock and organic compounds frozen together over billions of years. But they move fast and kinetic energy scales with the square of velocity. A comet entering the inner solar system from the Oort Cloud is falling from a tremendous height in gravitational terms, accelerating continuously as it approaches the Sun. By the time it crosses Earth's orbit, it may be travelling at 40 or 50 kilometers per second, far faster than any asteroid in a more circular orbit. A comet 5 kilometers across, travelling at 50 kilometers per second, carries enough kinetic energy to rival the total nuclear arsenal of humanity several times over. If it struck Earth, the impact would excavate a crater 100 kilometers across, throw enough debris into the atmosphere to darken the sky worldwide for months or years, trigger massive wildfires across entire continents, and potentially cause a mass extinction comparable to the one that ended the age of dinosaurs. This is not speculation. This is physics. We know what happened 66 million years ago when an asteroid roughly 10 kilometers across struck what is now the Yucatan Peninsula. We have the crater. We have the iridium layer in rocks around the world, the signature of extraterrestrial material spread across the planet by the impact. We have the fossil record, the abrupt disappearance of 3/4 of all species on Earth within a geological instant. We know what large impactors do, and the knowledge is sobering. A comet shower is not a guaranteed catastrophe, but it is a guaranteed increase in the probability of catastrophe. A slow-motion dice roll stretched across millions of years, each century bringing a slightly higher chance that something large and fast and frozen will fall from the sky and end whatever world exists below. The crucial point, the point that separates cosmic danger from cosmic doom, is time. The comet shower triggered by Gliese 710 will not begin for millions of years. The disturbed comets will not arrive for millions of years after that, and the shower itself will be spread across tens of millions of years, each individual comet arriving essentially at random, unpredictable in its timing, unpredictable in its trajectory, giving any civilization capable of tracking such objects ample time to identify threats and respond. We have, in a sense, been given advance warning of a hazard that will not arrive for longer than our species has existed. What we do with that warning is up to us, or up to whoever inherits our knowledge and our tools after we are gone. The Oort Cloud itself remains invisible, a theoretical construct made real only by the comets that escape from it and fall screaming into visibility as they approach the Sun. We cannot see the individual bodies drifting in that frozen wilderness. We cannot count them. We cannot know their exact distribution or their exact number. All we can do is watch the comets that emerge and work backward, inferring the existence and the structure of the source region from the behaviour of the messengers it sends. It is astronomy conducted at the limit of inference, science practiced at the very edge of the knowable, and it carries all the uncertainties that such frontier work implies. The estimates of Oort Cloud population range from 100 billion objects to several trillion. The estimates of its outer boundary range from 50,000 to 100,000 astronomical units. The estimates of the comet shower intensity that Gliese 710 will trigger vary by factors of 2 or 3, depending on the assumptions built into the models. We know the star is coming. We know it will disturb the comets. Beyond that, we are making educated guesses about a region of space we have never seen and cannot reach with any technology available to us, or plausibly available to us within the next few centuries. The darkness beyond Neptune is real. The frozen bodies drifting there are real. The star approaching from 62 light-years away is real. But our knowledge of how these elements will interact remains provisional, subject to revision as new observations refine our understanding of Gliese 710's trajectory, new models improve our simulations of gravitational perturbation, and new theoretical work deepens our understanding of the Oort Cloud structure. Science does not provide certainties about the distant future. It provides probabilities, ranges, confidence intervals, and within those ranges lies the authentic uncertainty of a universe that is not obligated to behave precisely as our models predict. What we can say with confidence is this: Gliese 710 represents the most significant known gravitational threat to the outer solar system within the foreseeable future. It is not the only star that will pass near the Sun. The galaxy is full of moving stars, and encounters are inevitable over astronomical timescales. But it is the closest passage we can currently predict, and the most likely to have measurable consequences. When it arrives, approximately 1.29 million years from now, it will graze the inner Oort Cloud at a distance that would be unremarkable for a star passing through open space, but is remarkably close by the standards of stellar astronomy. And in its wake, it will leave a disturbance that will echo through the solar system for the next 50 million years, a gravitational ripple spreading slowly inward, nudging comets out of their ancient orbits, sending them tumbling toward the light. The first of those disturbed comets will arrive in the inner solar system so far in the future that no human prediction can meaningfully address it. Will Earth still be inhabited? Will intelligent life still exist somewhere in the solar system? Will our descendants have spread to other stars, rendering the fate of this particular planetary system a matter of mere historical interest? These questions cannot be answered. They are not questions for astronomy. They are questions for hope, for imagination, for the kind of speculation that scientists are trained to avoid. All we can do is describe what will happen to the solar system itself, to the frozen debris circling in the outer darkness, to the comets that will fall and the star that will pass and the gravitational memory that will persist long after the encounter is over. And somewhere in that distant future, under a sky we cannot imagine, an observer might look up and see a comet falling. They might watch the ice sublimate in the heat of a star that is perhaps still the same yellow dwarf that warms Earth today. They might wonder, as humans have wondered for millennia, where the comet came from and what it means. And if their science is advanced enough, if their records reach back far enough, they might know the answer. They might trace the comet's orbit backward through time, accounting for every planetary perturbation, every gravitational nudge, until they arrive at a moment roughly 50 million years before their present. A moment when a small orange star passed within 10,000 astronomical units of the Sun. A moment when the frozen shell of the outer solar system was stirred ever so slightly, sending ripples inward through space and time. A moment that, from our perspective, lies more than 1 million years in the future, but from theirs is ancient history. The cause and effect are separated by abysses of time that dwarf the entire history of human civilization, and yet they are connected, linked by the patient mathematics of gravity, by the slow accumulation of orbital changes, by the endless falling of ancient ice toward the warmth of the Sun. The Sun, seen from the inner edge of the Oort Cloud, is barely distinguishable from the other stars. It is brighter, certainly, a point of light perhaps a magnitude or two more luminous than Sirius appears from Earth, but it is still just a point. No disk, no warmth, no obvious claim to being the gravitational master of everything within a light year. And yet it is. Its influence extends outward in every direction, thinning with distance but never quite vanishing, a sphere of sovereignty that encompasses trillions of frozen bodies, most of which have never felt the slightest brush of solar heat. This is the domain that Gliese 710 will enter. Not the familiar solar system of textbooks and planetary probes, but the vast, cold, almost incomprehensibly empty outer reaches where comets sleep in orbits that take millions of years to complete. To understand what the star's passage will do, we must first understand what exists out there, what the Oort Cloud actually is, how it formed, and why it matters. The Oort Cloud is a hypothesis that became a necessity. In the middle of the 20th century, astronomers faced a puzzle. Comets appeared in the inner solar system with orbital characteristics that made no sense if they had always been there. Long-period comets, the ones that sweep in from the outer darkness on trajectories taking thousands or millions of years, arrived from every direction. They were not confined to the plane of the planets. They came from above and below, from every angle of the celestial sphere, as if they were falling from a shell that surrounded the solar system uniformly. And their orbits often suggested that they were making their first passage through the inner solar system, that they had been dislodged from distant storage and were only now encountering the sun's warmth for the first time. Jan Oort, a Dutch astronomer, proposed the solution in 1950. He suggested that the solar system was surrounded by a vast spherical cloud of icy bodies, extending outward to perhaps 50,000 or even 100,000 astronomical units from the sun. These bodies were the remnants of the solar system's formation, planetesimals that had been flung outward by gravitational interactions with the giant planets during the chaotic early era, when Jupiter, Saturn, Uranus and Neptune were still settling into their current orbits. Too slow to escape the sun's gravity entirely, too energetic to remain in the inner solar system, they had ended up in a kind of gravitational limbo, bound to the sun but so loosely that the slightest disturbance could send them tumbling inward or outward. The theory explained everything. It explained why long-period comets came from all directions. They were falling from a spherical shell, not a flat disk. It explained why many seemed to be on their first inner system passage. They had been stored in deep freeze for billions of years and were only now being disturbed. It explained the steady trickle of new comets. External perturbations were constantly nudging some of them out of their stable orbits, sending them on the long fall toward the sun. The Oort Cloud was invisible, its individual members far too small and dark and distant to observe directly, but its existence was written in the orbits of every comet that appeared in Earth's sky. We now believe the Oort Cloud contains somewhere between several 100 billion and perhaps 2 trillion icy bodies larger than a kilometre across. The total mass is harder to estimate, but it is probably comparable to several Earth masses, an enormous amount of material when you consider the size of each individual object, but diffuse beyond comprehension when spread across a sphere more than a light year in diameter. If you were to travel through the Oort Cloud, you would see nothing. The average distance between objects is measured in tens of millions of kilometres. The cloud is less a cloud than an absence, a shell of statistical probability where objects exist but never encounter one another, never collide, never do anything except drift in slow orbits around a star that is merely the brightest point in a sky full of points. And yet this emptiness is not quite stable. The Oort Cloud exists at the edge of the sun's gravitational influence, where the pull of the galaxy itself becomes significant. Objects in the outer Oort Cloud experience tidal forces from the Milky Way's disk, gentle tugs that accumulate over millions of years and gradually shift orbital parameters. They also experience occasional encounters with passing stars, encounters that are normally distant enough to cause only minor perturbations but can sometimes, rarely, be close enough to reshape entire swathes of the population. Gliese 710's approach falls into that rare category. 10,000 astronomical units is close, extraordinarily close by the standards of stellar encounters. The average distance to the nearest star, as measured from the Sun at any given moment, is roughly 260,000 astronomical units. Most passing stars come no closer than tens of thousands of light-years worth of closest approach distance, still measurable, still capable of causing minor perturbations over long timescales, but nothing dramatic. Gliese 710 will pass within 4% of the current distance to Proxima Centauri. It will enter the Oort Cloud proper. It will move through a region where icy bodies actually exist, where its gravity will tug directly on millions of dormant comets, where its passage will leave a mark that persists for geological eons. The physics of this perturbation is straightforward in principle, but staggeringly complex in detail. As Gliese 710 approaches the solar system, its gravitational field will begin to interact with every object it passes. The strength of that interaction depends on distance, mass, and the geometry of the encounter. Objects on the near side of the Oort Cloud, the side facing the approaching stars, will feel a pull toward Gliese 710. Objects on the far side will feel less of a pull because they are farther away. This differential creates a tidal effect, a stretching of the entire cometary population along the axis of the star's approach. But the more important effect is the direct perturbation of individual orbits. Each comet in the Oort Cloud is following a long, slow elliptical path around the Sun. Most of these orbits are nearly circular at the moment, or rather, they have such enormous semi-major axes that the distinction between circular and elliptical becomes somewhat philosophical. A comet with an orbital period of 2 million years might have an aphelion at 20,000 astronomical units, and a perihelion at 15,000 astronomical units, making its orbit technically elliptical but functionally circular for most purposes. It has never come anywhere near the inner solar system. It has never felt the sun's heat. It has simply drifted for 4.5 billion years in the cold and the dark. When Gliese 710 passes, that comet will receive a gravitational nudge. The nudge might be tiny, a change in velocity measured in meters per second, perhaps even centimeters per second. But orbits in the outer Oort Cloud are so delicately balanced that tiny nudges have enormous consequences. A change in velocity of 1 meter per second, applied at the right point in an orbit with a period of millions of years, can shift the perihelion by thousands of astronomical units. It can transform an orbit that never approaches closer than 10,000 AU into an orbit that plunges all the way to the inner solar system. It can take a comet that has been invisible and inert since the formation of the solar system and send it falling toward the sun, where it will eventually blossom into a spectacle of gas and dust and streaming tails. This is what we mean when we talk about Gliese 710 disturbing the Oort Cloud. We do not mean that the star will smash through it like a bowling ball through pins. We do not mean that it will gravitationally capture comets or fling them into interstellar space in large numbers. We mean that it will change velocities by tiny amounts, shift orbital parameters by small fractions, and thereby alter the statistical distribution of where these objects will eventually go. The disturbance is subtle, almost gentle, but it operates on such an enormous population that even a small percentage of affected orbits translates to millions of individual comets with altered fates. Computer simulations of the encounter, using increasingly sophisticated models of the Oort Cloud structure and increasingly precise measurements of Gliese 710's trajectory, have attempted to quantify what this means. The results vary depending on assumptions about the Oort Cloud's density, its radial distribution, the masses of typical cometary nuclei, and the exact parameters of the stellar flyby. But the broad conclusions are consistent. Gliese 710's passage will increase the flux of long-period comets into the inner solar system by a factor that various studies have estimated at somewhere between 2 and 10 times the background rate. The peak of this increase will occur not during the encounter itself, but millions of years afterward, as the perturbed comets complete their long journeys inward, and the elevated flux will persist for tens of millions of years, gradually diminishing as the population of disturbed comets is depleted by successive passages through the inner solar system. The numbers involved are difficult to grasp. Under normal circumstances, perhaps 1 or 2 bright long-period comets appear in Earth's sky each year, comets with new orbits, falling from the Oort Cloud, making their first or second passage through the inner solar system. This is the background rate, the steady trickle that has persisted throughout recorded history. If Gliese 710 doubles that rate, we might expect 2 to 4 such comets per year during the peak of the disturbance. If it quintuples the rate, 5 to 10, these are still rare events by human standards, a memorable comet every few months rather than every year, but they represent an enormous change by astronomical standards, a measurable shift in the habitability and hazard profile of the inner solar system. And here we must pause to address the question that lurks beneath all of this discussion, the question that makes people pay attention when they hear about stars passing close to the sun, the question of danger. Will Gliese 710's passage cause a comet impact on Earth? Will it trigger a mass extinction? Will it end human civilization, or whatever civilization might exist 1.5 million years from now? The honest answer is, probably not, but we cannot be certain, and the risk is not zero. Cometary impacts on Earth are rare. The planet is small, space is large. Most comets that enter the inner solar system never come anywhere near Earth. They loop around the sun, lose some of their ice to sublimation, and return to the outer darkness, or they gradually fragment and disperse into streams of debris that produce meteor showers when Earth crosses their paths. A comet striking Earth requires a precise alignment of orbital parameters that is statistically unlikely for any given comet. But statistically unlikely is not the same as impossible, and when you multiply small probabilities by large numbers of events, you get non-negligible risks. If Gliese 710's passage sends 10 million additional comets into the inner solar system over the following 50 million years, and some estimates suggest numbers in this range, then the probability that at least one of those comets will strike Earth becomes significant, not certain, not even particularly likely for any given million-year window, but possible, plausible, the kind of risk that actuaries and planetary scientists take seriously, even if it lies far beyond any planning horizon that matters to human institutions. The geological record suggests that comet impacts, while rarer than asteroid impacts, do occur. The boundary between the Eocene and Oligocene epochs, roughly 34 million years ago, shows evidence of multiple impacts occurring in a relatively short geological window. Multiple craters, multiple tektite-strewn fields, multiple signatures of extraterrestrial material in the sedimentary record. Some researchers have suggested that this was the result of a comet shower, a period of elevated cometary flux caused by a stellar encounter or some other disturbance of the Oort Cloud. The evidence is controversial, the interpretation disputed, but the possibility that Earth has experienced such episodes in the past makes it plausible that it will experience them again in the future. What we cannot do is predict which specific comets will be disturbed, which specific orbits will bring them to Earth-crossing trajectories, which specific moments in the next 50 million years will see impacts occur. The chaos is genuine. The sensitive dependence on initial conditions, on the exact positions and velocities of trillions of objects, on the precise trajectory of Gliese 710, on the gravitational influences of other stars that will pass in the intervening eons, makes detailed prediction impossible. We can speak only of probabilities, of elevated risks, of statistical expectations. The specifics will emerge only as the future unfolds, and by then, the observers will be so far removed from our present that our predictions will be ancient history, quaint artifacts of a civilization that existed before the star even arrived. This uncertainty is not a failure of science, it is a reflection of reality. The universe is not deterministic at the level of practical prediction, not for systems this complex and timescales this long. The best we can do is understand the mechanisms, estimate the probabilities, and acknowledge that the future will surprise us in ways we cannot anticipate. But let us return to the encounter itself, to the moment when Gliese 710 makes its closest approach. Let us try to imagine what that moment might be like if there were observers present to witness it. The star will not arrive suddenly. Its approach will be visible for millennia before the closest passage, a gradual brightening in whatever constellation it occupies at that distant time. From Earth, if Earth is still inhabited, if telescopes still point at the sky, observers will watch it grow from a dim red point to a bright orange presence, eventually reaching a magnitude that makes it one of the more prominent stars in the night sky. Not brilliant, not overwhelming. Gliese 710 is a small star, only about 60% as massive as the Sun, perhaps 40% as luminous. At its closest approach of roughly 10,000 AU, it will shine with an apparent magnitude of perhaps 0 or -1, comparable to the brightest stars, but not the overwhelming spectacle that a closer or more luminous star would present. The motion will be visible. Over the course of years, observers will be able to watch Gliese 710 drift against the background of more distant stars, its proper motion accelerated by its proximity. A patient observer with a good telescope could track its nightly progress, watching it slide across the celestial sphere at a rate unprecedented for any star in recorded history. No other object in the sky except the Sun, Moon, and planets will have shown such obvious motion. It will be a visceral demonstration that the stars are not fixed, that the galaxy is a churning river of motion, that our solar system is merely one eddy in a flow that never stops, and then it will recede. The closest approach will pass, a moment that takes perhaps a few decades to unfold as the star traces its hyperbolic path through the Oort Cloud and curves away toward interstellar space. The brightness will fade. The proper motion will slow. Within a few centuries, Gliese 710 will be just another dim star, retreating into the cosmic background, leaving nothing behind except the gravitational memory of its passage. That memory, written in the altered orbits of countless icy bodies, will take millions of years to express itself in the inner solar system. The timescale is almost impossible to conceptualize. Consider that modern humans have existed for roughly 300,000 years. Consider that agriculture, writing, cities, all of recorded history, all of civilization, occupies perhaps the last 10,000 years. Consider that the interval between Gliese 710's closest approach and the arrival of its first disturbed comets at Earth's orbit could be 50,000 years. 5 times the span of human civilization, an interval in which entire species could evolve and go extinct, in which ice ages could come and go, in which the very geography of Earth could shift as continents drift and mountains rise and erode, and the peak disturbance is farther still, 10 million years after the encounter, 20 million. The models vary, but the timescales are geological, evolutionary, planetary. We cannot meaningfully discuss what Earth will be like then. We cannot predict whether humans will exist, whether intelligence will persist, whether any observer will remain to watch the comets fall. All we can do is trace the physics forward, calculate the perturbations, note that the consequences of today's approaching star will still be unfolding when our present is as ancient as the dinosaurs are to us. This is the strange temporal texture of astronomical events. They unfold across timescales that dwarf everything we know, everything we can plan for, everything we can meaningfully affect. Gliese 710 is already on its way. It has been approaching the solar system for millions of years, and it will continue approaching for another 1.229 million years until the encounter occurs. The perturbations have, in some sense, already been determined. The star's trajectory is set by the laws of gravity. The Oort Cloud's response is fixed by the same laws. The future is implicit in the present, even if we cannot calculate it in detail, and yet the consequences will not be felt for eons. The cause precedes the effect by intervals that make causation itself seem almost meaningless, a cosmic Rube Goldberg machine in which the trigger and the outcome are separated by abysses of empty time. What do we do with such knowledge? What response is appropriate when confronted with a threat, if threat is even the right word, that will not materialize for 50 million years? The honest answer is that we do nothing, not because the knowledge is useless, but because the timescale removes it from the domain of action and places it firmly in the domain of understanding. We study Gliese 710 not because we plan to do something about it, but because understanding the solar system's future helps us understand its past. The same processes that will send comets cascading inward after Gliese 710's passage have been operating throughout the solar system's history. Other stars have passed by before. Other disturbances have stirred the Oort Cloud. The comets we see today, the long-period visitors that occasionally grace our skies, are the echoes of past encounters, past perturbations, past gravitational ripples propagating through the frozen shell of the outer solar system. By studying what Gliese 710 will do, we illuminate what has already happened. We connect the present to the deep past. We place our solar system in the context of the galaxy's churning motion. We understand that Earth is not an isolated world, but a participant in a cosmic dance that has been unfolding for billions of years and will continue for billions more. The knowledge has value not because it changes our behavior, but because it changes our understanding. And understanding, in the end, is what science is for. There is something almost meditative about contemplating events on these timescales. The urgencies of daily life, the political crises and economic fluctuations and personal anxieties that consume our attention shrink to insignificance when measured against the patient approach of a star that will not arrive for a million years. The perspective is not escapist. The immediate problems are still real and still require our attention, but it is grounding. It reminds us that the universe operates on rhythm far slower than human experience, that most of cosmic history is waiting, that the dramatic events we read about in astronomy textbooks are separated by vast stretches of quiet in which nothing much happens and stars simply drift through the void, approaching their appointments with other stars at velocities that seem fast by earthly standards but are glacial when measured against the distances involved. Gliese 710 is moving toward us at roughly 15 kilometers per second relative to the Sun. This is faster than any bullet, faster than any spacecraft humanity has ever launched. And yet, from the star's perspective, if a star could have a perspective, the journey to the solar system is almost impossibly slow. At 15 kilometers per second, it takes roughly 20,000 years to travel a single light year. The star must cross roughly 60 light years between its present position and its closest approach. The journey takes 1.29 million years. Each year, Gliese 710 moves roughly 0.47 light years closer to the Sun. Each decade, roughly 0.27 light years. Each century, roughly 0.40 light years. The progress is measurable, but almost imperceptible. A slow drift that will continue for thousands of human generations before the encounter finally occurs. We are watching the slow-motion beginning of an event whose ending lies beyond the horizon of meaningful prediction. We are witnesses to the opening act of a drama that will take millions of years to unfold, and we are perhaps the only observers who will ever understand the full scope of what is happening, the only intelligence in this particular corner of the galaxy that has developed the science to predict the encounter and the imagination to contemplate its consequences. Whatever comes after us, whatever intelligences might exist when Gliese 710 arrives, or when the disturbed comets finally fall, they will inherit the consequences without necessarily understanding the cause. They might rediscover the connection, trace the orbits backward, reconstruct the encounter from the evidence it leaves behind, or they might simply watch the comets fall without knowing why, accepting the universe as they find it, unaware that the show was set in motion before their species even existed. This is the peculiar privilege of our moment in time. We stand at a point in history where we can see both backward and forward, where we can trace the solar system's past through the crater record and the comet populations, and where we can project its future through the approaching star and the simulations of what its passage will bring. We are briefly, improbably, aware of our place in the galaxy, aware of the processes that shape our cosmic neighbourhood, aware that the quiet sky above us is an illusion, a snapshot of a system in constant motion, a frozen moment in a drama that has been unfolding for billions of years and will continue long after our species is gone. The star keeps approaching, the comets keep waiting in the dark, and time, indifferent to our awareness, continues its slow accumulation, carrying us all forward toward an encounter that is already as certain as anything in the universe can be. The certainty itself deserves examination. We speak of Gliese 710's approach as though it were written in stone, as though the trajectory were fixed and immutable, a line drawn across space-time that the star must follow without deviation. And in a sense, this is true. The gravitational forces that govern stellar motion are deterministic. Given perfect knowledge of every mass in the galaxy and its precise position and velocity, one could in principle calculate the future of every star forever. But we do not have perfect knowledge. We have measurements, and measurements have errors, and errors compound over time like interest on a loan, growing larger with each passing year until the precision of our predictions dissolves into uncertainty. The Gaia spacecraft, which provided the data confirming Gliese 710's close approach, measured the star's position and motion with extraordinary precision, but extraordinary is not infinite. There are error bars on every number, tiny ranges of uncertainty that reflect the limits of our instruments and the inherent difficulty of measuring objects moving at cosmic velocities across cosmic distances. For Gliese 710, these uncertainties are small enough that the close encounter is essentially guaranteed. The star will pass somewhere between roughly 4,000 and 16,000 astronomical units from the Sun, with the most probable distance somewhere around 10,000 AU. This is a range, not a point. The star's path is not a single line but a fuzzy corridor, a zone of possible trajectories that narrow as we refine our measurements, but never quite collapse to a single definite track. This uncertainty matters because the consequences of the encounter depend sensitively on the details. A passage at 4,000 AU would be dramatically closer than a passage at 16,000 AU, would disturb the Oort Cloud far more severely, would send far more comets cascading inward on potentially dangerous trajectories. The difference between the close end of the range and the far end could be the difference between a moderate perturbation and a significant shower, between a few hundred extra comets per century and a few thousand. We know the encounter will happen. We cannot yet say exactly how intense it will be. The uncertainty will shrink over time. Each new observation of Gliese 710 adds another data point, another constraint on its trajectory, another refinement of our predictions. Space telescopes yet to be built will measure the star's position and velocity with greater precision than Gaia could achieve. Ground-based observatories will track its motion year after year, decade after decade, gradually narrowing the corridor of possibility until the encounter becomes as precisely defined as any future event can be. By the time Gliese 710 is 100,000 years away, still unfathomably distant by human standards, but much closer than it is now, our descendants, if they still exist and still practice astronomy, will know its trajectory with exquisite precision. They will be able to predict its closest approach to within a few astronomical units, will know almost exactly which regions of the Oort Cloud will be most disturbed, We'll perhaps even be able to identify specific comets that will be sent sunward by the encounter. But this assumes continuity. This assumes that the knowledge we are accumulating now will be preserved and extended, that the observations will continue, that someone will still be watching. 100,000 years is a long time. It is longer than our species has existed in anything like its current form, longer than the entire span of recorded history multiplied a dozen times over. Civilizations have risen and fallen in far less time. Technologies have been invented and forgotten. Languages have emerged, flourished, transformed beyond recognition, and vanished entirely. What guarantee do we have that the astronomical knowledge of 2024 will survive into the deep future? That our observations of Gliese 710 will be preserved and understood? That our predictions will be remembered by those who might actually witness the encounter? None. We have no guarantee at all. The continuity of human knowledge is fragile, dependent on institutions and technologies and social structures that have never been tested over such timescales. Libraries burn, servers fail, languages change. The very concept of astronomical observation might become obsolete if our descendants develop technologies that make our current methods seem as primitive as using sticks to measure shadows, or humanity might simply end, extinguished by any of the countless threats that could destroy a species. Asteroid impacts, supervolcanoes, engineered pandemics, nuclear war, ecological collapse, or simply the slow grinding down of a civilization that loses interest in its own perpetuation. The knowledge of Gliese 710's approach might die with us, might have to be rediscovered by whatever comes next, might be lost forever if nothing comes next. This is the strange pathos of long-term prediction. We know something remarkable about the future, something that took centuries of astronomical development to discover, and decades of precise measurement to confirm. We know that a star is coming, that the Oort Cloud will be disturbed, that comets will fall, and yet this knowledge may have no practical value at all. It cannot help us prepare for an event a million years away. It cannot warn our distant descendants, who may not exist or may have no way of receiving our warning. It is knowledge for its own sake, a testament to human curiosity rather than human utility. A message we send into the void with no expectation that anyone will be listening when the event finally occurs. And yet there is something beautiful in the attempt. There is something noble about a species that bothers to track the motions of distant stars, that calculates encounters millions of years in the future, that contemplates consequences it will never experience. The knowledge may be useless in any practical sense, but it is not meaningless. It tells us something about ourselves, about what we value, about the kind of creatures we are. We are the species that looks up. We are the species that asks questions whose answers lie beyond our lifetimes, beyond our civilizations, beyond perhaps the existence of our kind. We are the species that refuses to be bounded by the horizon of our own mortality, that insists on understanding the universe even when that understanding brings us face to face with our own insignificance. Gliese 710 will arrive whether we watch it or not. The comets will fall whether we predict them or not. The solar system will continue its slow evolution through galactic space, encountering stars and nebulae and gravitational perturbations, regardless of whether any intelligence is present to observe and understand. Our knowledge does not change the universe, but it changes us. It makes us participants in the cosmic drama rather than mere passengers, actors who understand our roles even if we cannot control the script. The trajectory continues, day by day, year by year, the star drifting closer at its implacable 15 kilometers per second. And somewhere in the outer darkness, the Oort Cloud waits, patient and cold, its trillions of icy bodies circling the sun on orbits so vast that a single revolution takes millions of years. These are the oldest unchanged relics of the solar system's birth, frozen remnants from the primordial disk of gas and dust that coalesced into planets 4.5 billion years ago. They have been out there, in the cold and the dark since before life existed on Earth. They were already ancient when the first single-celled organisms appeared in our planet's oceans. They have outlasted every mass extinction, every evolutionary revolution, every geological era. They are survivors, in the most profound sense of the word, objects that have endured essentially unchanged while the inner solar system transformed beyond recognition. The comets of the Oort Cloud are made of the same materials that form the Sun and planets. hydrogen compounds frozen into ice, carbon compounds darkened by billions of years of cosmic ray bombardment, silicate grains and organic molecules, and traces of heavier elements forged in long-dead stars. They are time capsules, preserving the chemistry of the early solar system in a way that nothing else can. When a comet falls inward and passes close to the Sun, the heat vaporizes its surface, releasing gases that carry these ancient materials into space where we can analyze them with spectroscopes. Every comet is a message from the deep past, a sample of the material that built our world, preserved in the cosmic freezer for 4 billion years, and finally delivered to us by the accidents of gravitational perturbation. Most comets that reach the inner solar system come from a region closer than the Oort Cloud proper, from the scattered disk and the Kuiper belt, populations of icy bodies that orbit at tens or hundreds of astronomical units, rather than thousands or tens of thousands. These are the short-period comets, objects like Halley's Comet and Comet Encke, that return every few decades or centuries, their orbits shaped by encounters with the giant planets and the accumulated gravitational tugging of countless close approaches to the Sun. They are veterans of the inner solar system, bodies that have been cycling through the warm regions for millennia, losing mass with each passage as the Sun's heat boils away their surfaces. Eventually they exhaust their volatile materials and become inert, indistinguishable from asteroids except for their icy cores, ghost comets that no longer produce the spectacular tails that made them famous. The Oort Cloud comets are different. They come from so far out that they have never felt the Sun's warmth, have never lost material to solar heating, have never been processed by the inner solar system's more energetic environment. When an Oort Cloud comet falls inward for the first time, it is pristine, its surface untouched by anything except the slow rain of cosmic rays and the occasional collision with another body in the outer darkness. These are the long-period comets, objects that take thousands or millions of years to complete a single orbit, that plunge through the inner solar system in a matter of months and then retreat into the darkness for another epic journey around their impossibly elongated paths. Some of these comets become famous. Comet Hale-Bopp, which graced our skies in 1997, came from the Oort Cloud, falling inward after a journey that began when our ancestors were still learning to farm. Its orbit carries it out to about 370 astronomical units at its farthest point. Not quite into the Oort Cloud proper, but far enough that it will take roughly 2,500 years to return. Comet McNaught, which blazed across the southern hemisphere in 2007, also came from the distant reaches of the solar system, a visitor from the cold that briefly lit up our skies before retreating into the darkness. These comets are rare precisely because they come from so far away. The Oort Cloud is vast but sparsely populated, and the gravitational perturbations that send comets sunward are infrequent. Most Oort Cloud comets orbit peacefully in the darkness, undisturbed for billions of years, waiting for the random gravitational nudge that will finally send them falling toward the Sun. Gliese 710 will provide that nudge on an unprecedented scale. When it passes through the outer Oort Cloud, its gravity will act like a cosmic hand sweeping through a cloud of dust motes, stirring them from their ancient orbits and setting them on new paths. Some of these new paths will carry the comets outward, ejecting them from the solar system entirely, sending them drifting into interstellar space to wander the galaxy forever. Others will carry the comets inward, their orbits transformed from nearly circular to highly elliptical, their paths now aimed at the distant spark of the Sun. These are the comets that will eventually reach the inner solar system, the bodies that will streak across Earth's skies millions of years from now, the visitors that our distant descendants might see without knowing their origin. The physics of the perturbation is straightforward enough that we can model it with reasonable confidence. As Gliese 710 approaches, its gravitational pull begins to affect comets in the outer Oort Cloud, tugging on them, altering their velocities by tiny amounts. The closer the star passes to a given comet, the stronger the perturbation. Comets near the star's path will be dramatically affected, while those on the far side of the Oort Cloud will barely notice its presence. The perturbation is not instantaneous. The star passes slowly, taking thousands of years to traverse the Oort Cloud, and the gravitational effects accumulate over time. It is a slow reshuffling rather than a sudden impact, a gradual redistribution of orbital energies that plays out over millennia. The result is a wave of disturbed comets, bodies whose orbits have been altered by the passing star. Some of these will begin falling inward almost immediately, their new trajectories carrying them toward the Sun on timescales of hundreds of thousands of years. Others will enter orbits so elongated that they won't return to the inner solar system for millions of years. Still others will be left on unstable trajectories, gradually evolving under the influence of other perturbations until they too eventually fall sunward or escape entirely. The encounter is not a single event but a trigger, a disturbance that sets in motion a chain of consequences extending far into the future. Simulations of the encounter suggest that the comet flux in the inner solar system could increase by roughly 50% at its peak, which will occur several million years after the closest approach. This is significant but not catastrophic, roughly 1.5 times as many comets passing through the region where Earth orbits, roughly 1.5 times the current probability that a comet will strike our planet in any given year. The current impact rate is already low. Increasing it by 50% still leaves the danger manageable by cosmic standards. Earth has survived far worse. Earth will almost certainly survive this, but survival is not the same as immunity. Even a moderate increase in the comet flux means more opportunities for collision, more chances that a body will arrive on a trajectory that intersects Earth's orbit at precisely the wrong moment. Over millions of years, these small increases in probability accumulate. An event that has a 1 in a million chance of happening in any given year becomes likely over 1 million years, nearly certain over 10 million. The comets disturbed by Gliese 710 will be falling for tens of millions of years, and during all that time the dice will be rolling, each falling comet another chance for an encounter with the inner planets. The comets themselves are dangerous not because they are large, most are relatively small, a few kilometers across at most, but because they are fast. A comet falling from the Oort Cloud picks up tremendous speed as it descends into the Sun's gravitational well, reaching velocities of tens of kilometers per second by the time it crosses Earth's orbit. An impact at such velocities releases enormous energy, far more than the same mass travelling at the relatively sedate speeds of near-Earth asteroids. A comet a few kilometers across, striking Earth at 50 kilometers per second, would release energy equivalent to billions of nuclear weapons, would blast a crater hundreds of kilometers wide, would throw enough debris into the atmosphere to darken the skies and plunge the planet into an impact winter lasting years or decades. This is the scale of the Chicxulub impact, the event that ended the reign of the dinosaurs 66 million years ago. This is what a comet can do. The probability of such an impact is low, but not zero. It is higher during a comet shower, when the flux through the inner solar system is elevated, and it remains elevated for millions of years after a close stellar encounter. The geological record suggests that Earth has experienced multiple episodes of increased cratering activity over its history, some of which correlate with known or suspected stellar passages. The connection is difficult to prove, the evidence is fragmentary, the timing uncertain, the alternative explanations numerous, but the pattern is suggestive. Close stellar encounters may have shaped Earth's history more than we realise, may have contributed to mass extinctions and evolutionary upheavals, may have helped determine which species survived and which perished at critical moments in the history of life. Gliese 710 will add another chapter to this story. Millions of years from now, when the disturbed comets finally reach the inner solar system in significant numbers, Earth, or whatever Earth has become by then, will face an elevated risk of impact. The sky will be slightly busier, the long-period comets slightly more frequent, the cosmic environment slightly more hazardous. It will not be an apocalypse, it will not be a catastrophe. It will be a subtle shift in the odds, a minor elevation of risk persisting over geological timescales, a reminder that the solar system is not a static place but a dynamic environment shaped by forces we're only beginning to understand, and the comets that fall will carry with them their ancient cargo, their frozen remnants of the early solar system, their messages from the time before planets. If intelligence still exists when they arrive, human or otherwise, Earth-based or scattered across the solar system, it might study them, might analyse their composition, might learn from them secrets about the solar system's origin that we cannot yet imagine. Each comet is a sample, a piece of the primordial disk, a fragment of the raw material from which everything we know was built. The disturbance caused by Gliese 710, for all its potential danger, will also be an opportunity, a chance to study pristine material that would otherwise have remained frozen in the outer darkness forever. The waiting continues. The star moves closer. The comets orbit in patient silence. And in that silence, something profound is already happening, something that requires no stellar visitor to set in motion, something woven into the very fabric of where we are and when we are in the story of our galaxy. The Oort Cloud, that vast and diffuse halo of frozen wanderers, is not merely waiting for Gliese 710. It is perpetually waiting, perpetually vulnerable, perpetually subject to influences that operate on timescales so immense they make human history seem like the flutter of a mayfly's wing. To understand what Gliese 710 will do, we must first understand what is always being done, the ceaseless tidal kneading that shapes the outer solar system even in the absence of any nearby star. The Milky Way itself is the great sculptor. Our galaxy is not a static arrangement of stars but a vast rotating structure, a flattened disk of matter embedded in a spherical halo, the whole assembly turning with a period of roughly 230 million years. The Sun, along with its entire retinue of planets and moons and asteroids and comets, orbits the galactic centre at a distance of roughly 26,000 light-years, travelling at a speed of approximately 220 kilometers per second. This orbital motion carries us through regions of varying stellar density, past molecular clouds and spiral arms, through the thin galactic disk and occasionally above or below it in a gentle bobbing motion. And all of this motion has consequences for the outermost reaches of the solar system. The galactic tide is a subtle but relentless force. Just as the moon raises tides on Earth by exerting slightly different gravitational pulls on different parts of our planet, so too does the mass distribution of the galaxy exert slightly different pulls on different parts of the solar system. The effect is imperceptible for the inner planets, negligible even for the Kuiper belt, but for the Oort Cloud, it is significant. The galactic tidal field stretches and compresses the cloud over millions of years, altering the orbits of its constituent comets, occasionally nudging them onto trajectories that send them plunging inward. This is not a dramatic process. It is not a sudden perturbation. It is a slow, grinding, perpetual reshaping, a background hum of gravitational influence that has been operating since the cloud first formed 4.5 billion years ago. The mathematics of this tidal influence are elegant in their simplicity. The galactic disk, which contains most of the galaxy's visible mass, exerts a vertical component of gravitational force that varies with distance from the galactic plane. When the solar system is exactly in the plane, this vertical force is zero. As we bob above or below the plane in our slow oscillation, the force increases, pulling us back toward the middle. This oscillation has a period of roughly 60 to 70 million years, and it creates a corresponding oscillation in the strength of the galactic tide felt by the Oort Cloud. Some researchers have suggested that this oscillation may correlate with periodic increases in comet flux to the inner solar system, perhaps even with periodic mass extinctions on Earth, though this hypothesis remains controversial and the evidence incomplete. The point is not whether this specific correlation is real. The point is that the Oort Cloud exists in an environment of perpetual perturbation. Even if no star ever passed near the Sun, the galactic tide would continue to send comets inward, would continue to erode the cloud's edges, would continue to reshape its structure over billions of years. Gliese 710 is not introducing something new. It is amplifying something that already exists, adding its voice to a chorus that has been singing since before life arose on Earth. And there are other voices in that chorus. The giant planets of our own solar system, though they orbit far inside the Oort Cloud, exert their own subtle influence on the comets that venture inward. When a comet falls toward the Sun from the outer darkness, it must run a gauntlet of gravitational encounters. Jupiter, with its enormous mass, is the primary gatekeeper. A comet approaching the inner solar system may pass close enough to Jupiter to have its orbit significantly altered, may be flung onto a shorter period orbit that keeps it closer to the Sun, may be ejected from the solar system entirely, or may be nudged onto a trajectory that sends it diving into the Sun itself or crashing into one of the inner planets. Saturn, Uranus and Neptune play similar though lesser roles, their gravitational influences adding complexity to the orbital dynamics of incoming comets. This means that even when the Oort Cloud releases a surge of comets, as it will after Gliese 710's passage, those comets do not simply fall straight toward Earth in a predictable stream. They are scattered, redirected, delayed, accelerated, captured or expelled by the complex gravitational environment of the planetary system. Some comets that begin their inward journey in the immediate aftermath of the stellar passage will take only a few million years to reach the inner solar system. Others will be caught in orbital resonances will be bounced between planets, will take tens of millions of years to complete their journey. Still others will never arrive at all, will be ejected back to the outer darkness or cast entirely out of the solar system, will become interstellar wanderers like the mysterious object Oumuamua that briefly visited us in 2017. The comet shower triggered by Gliese 710A therefore will not be a discrete event but a prolonged era of elevated activity, a statistical increase in comet flux that may last for 50 million years or more. This is important for understanding the actual risk posed by the encounter. If all the disturbed comets arrived at once, in a concentrated barrage lasting a few thousand years, the danger would be severe. But spread over tens of millions of years, the elevated flux becomes a background condition rather than an acute crisis. The probability of impact in any given century or any given millennium remains small. It is the cumulative probability over deep time that becomes significant, and that cumulative probability must be weighed against the countless other risks that Earth faces over such immense timescales. Consider what else might happen in the 50 million years following Gliese 710's closest approach. The continents will continue their slow dance, driven by the convection currents in Earth's mantle. North America and Eurasia may merge into a new supercontinent. The Atlantic Ocean may close, mountain ranges will rise and erode, the climate will fluctuate through ice ages and warm periods, through configurations of ocean currents and atmospheric composition that we cannot predict. Life will continue to evolve, species arising and going extinct in response to environmental pressures that have nothing to do with comets. Volcanic eruptions will occur, some of them catastrophic. The sun will continue its slow brightening, gradually increasing Earth's surface temperature, eventually making the planet uninhabitable for life as we know it, though this final reckoning is still roughly 1 billion years away. Against this backdrop of perpetual change, the comet shower is just one factor among many. One thread in a tapestry of risk and transformation that extends across geological time. It is not uniquely dangerous. It is not especially likely to be the specific cause of any particular catastrophe. It is simply part of the cosmic context in which Earth exists, has always existed, will continue to exist until the sun swells into a red giant and swallows the inner planets whole. And yet there is something compelling about the specificity of Gliese 710. Something that captures the imagination in a way that abstract discussions of galactic tides and background comet flux do not. We know this star. We have measured its position and velocity with extraordinary precision. We can predict its future trajectory with confidence extending over millions of years. We can name it, can point to it in the sky, can say with certainty that in 1.29 million years it will be there, closer to us than any other star for millions of years before or after. This specificity transforms an abstract statistical risk into a concrete future event, an appointment written in the laws of physics, a date marked on a calendar that extends far beyond any human planning horizon. The knowledge itself is remarkable. For most of human history, the stars were fixed points of light, unchanging and eternal, their motions imperceptible over human lifetimes. The ancient astronomers tracked the wandering planets, noted the occasional appearance of comets, recorded the rare and terrifying spectacle of novae and supernovae. But the stars themselves seemed frozen in their constellations, the same patterns that had shone down on the first humans shining down unchanged on their distant descendants. This was an illusion born of the brevity of human life. The stars do move, they orbit the galactic centre, they drift relative to one another, they approach and recede over timescales that dwarf the entire span of recorded history. But only in the past few decades have we developed the instruments precise enough to measure these motions in detail, to track the three-dimensional trajectories of nearby stars, to peer into the future and see which ones will draw near. The Hipparcos satellite, launched by the European Space Agency in 1989, was a pioneer in this work. For nearly 4 years, Hipparcos measured the positions and proper motions of over 100,000 stars with unprecedented accuracy, mapping the local stellar neighbourhood in 3 dimensions for the first time. It was Hipparcos data that first identified Gliese 710 as a future close encounter, that first predicted its approach to within roughly 1 light-year of the Sun in a little over 1 million years. The uncertainty in this early prediction was considerable. The error bars on the closest approach distance spanned a range from nearly 0 to well over a light-year, but the basic conclusion was clear. This star was coming, and it was coming closer than most. The Gaia mission, launched in 2013 and still operating today, has transformed our understanding of stellar motions. Gaia has measured the positions, distances and proper motions of nearly 2 billion stars with accuracies that make Hipparcos look like a crude first attempt. For nearby stars like Gliese 710, Gaia's measurements have reduced the uncertainties by an order of magnitude or more. We now know that the closest approach will occur in approximately 1.29 million years, give or take a few tens of thousands of years. We know that the minimum distance will be roughly 10,000 astronomical units, with an uncertainty of perhaps 1,000 astronomical units in either direction. We know the star's mass, its luminosity, its spectral type, its velocity through space. We have, in effect, a fairly detailed portrait of the cosmic bullet that is heading our way. This knowledge raises questions that extend beyond astronomy into philosophy, into the realm of how we think about time and risk and our place in the universe. What does it mean to know about a danger that lies more than 1 million years in the future? How should this knowledge affect our present actions, if at all? Is there any meaningful sense in which we can prepare for an event that will occur long after every human being alive today has been dead for over 1 million years? The honest answer is that we probably cannot prepare, at least not in any direct way. We have no technology that could deflect a star, no conceivable method for altering Gliese 710's trajectory or preventing its gravitational influence on the Oort Cloud. We could perhaps develop better methods for detecting and deflecting individual comets, could hone our planetary defense capabilities so that our descendants, whoever or whatever they might be, would have a better chance of intercepting any comets that threatened Earth. But this is a goal that makes sense regardless of Gliese 7 to 10. The threat from comets and asteroids exists now, has always existed, will continue to exist whether or not any particular stellar passage amplifies it. The knowledge of Gliese 7 to 10's approach is, in this sense, not actionable. It tells us something we cannot change, something we must simply accept as part of the cosmic environment we inhabit. But there is another way to think about this knowledge, a way that does not depend on practical action. The knowledge of Gliese 710 is a reminder. It reminds us that the universe is not arranged for our convenience, that events unfold on timescales that mock human planning, that the forces shaping our world operate with a patience and persistence that we can barely comprehend. It reminds us that Earth is a small island in an immense ocean of space and time, subject to influences that originate light years away and play out over millions of years. It reminds us that we are not the centre of the story, that the story was in progress long before we arrived and will continue long after we're gone, that our brief moment of awareness is a tiny window onto a narrative that spans billions of years. This reminder has value even if we can do nothing about it. It cultivates a perspective that is at once humbling and exhilarating, a perspective that situates our human concerns within a vastly larger context. The wars and famines and technological revolutions that consume our attention, the political conflicts and economic anxieties that fill our news cycles, the personal dramas and triumphs and sorrows that make up our individual lives, all of these are real and important, but they are also small, transient, ephemeral compared to the slow processes that shape the solar system over geological time. This is not a counsel of despair. It is an invitation to wonder, a call to appreciate the extraordinary fact that we exist at all, that we have emerged from the cosmic process and developed the capacity to understand it, that we can sit here on this pale blue dot and contemplate the approach of a star that will not arrive for 1 million years. The star does not care about us. It has no awareness, no intention, no concern for the fate of the comets it will disturb or the planets those comets might strike. It is simply moving through space, following the laws of gravity, tracing the path that was determined by its initial conditions when it formed billions of years ago. But we can care about it. We can study it, track it, predict its future trajectory, understand its properties, place it within the context of stellar evolution and galactic dynamics. This capacity for understanding is perhaps the most remarkable thing about our species, more remarkable than our tools or our social structures or our artistic achievements. We are the part of the universe that has learned to contemplate itself, to model its own dynamics, to peer into its own past and future with increasing accuracy. Gliese 710 is, in this sense, a gift. It gives us something concrete to think about, a future event that we can analyse and discuss and use as a lens for examining deeper questions about time and risk and cosmic context. It connects our present moment to a future so distant that imagining it requires a deliberate act of intellectual stretching. It forces us to confront the limits of our knowledge and our power, to acknowledge that some things lie beyond our control even as they lie within our understanding, and it invites speculation about what might exist in that distant future. Will humans still be here in 1.29 million years? Will intelligence of some kind persist, whether biological or artificial or some hybrid form we cannot yet imagine? Will there be minds capable of observing Gliese 710 as it blazes through the night sky, closer and brighter than any star since the Sun itself? Will there be astronomers tracking the disturbed comets, planetary defenders standing ready to intercept any that threaten inhabited worlds, historians looking back at our era and marvelling at how little we understood? We cannot know. The uncertainty extends not just to the physical events, but to the entire trajectory of life and intelligence on Earth and beyond. Perhaps humanity will have gone extinct by then, wiped out by some catastrophe we failed to prevent or simply faded away through gradual decline. Perhaps we will have transformed into something unrecognizable, uploaded our minds into vast computer networks or merged with artificial intelligences or spread across the galaxy in forms we cannot imagine. Perhaps we will have left the solar system entirely. We'll be watching Gliese 710's approach from observatories circling distant stars. We'll regard the Sun and its cometary halo as ancient history rather than present concern. The only certainty is the star itself, moving inexorably closer, indifferent to our speculations, committed to its trajectory by the laws of physics that govern all matter in the universe. Whatever else happens, whatever triumphs or tragedies unfold, whatever civilizations rise and fall in the million years to come, Gliese 710 will continue its approach, will reach its closest point, will recede again into the stellar background, leaving behind its signature in the disturbed orbits of 1 trillion frozen worldlets. This is the deep rhythm of cosmic time, the pulse beneath the pulse, the heartbeat of a universe that operates on scales we can measure but barely grasp. And perhaps that is enough. Perhaps the act of grasping, however imperfectly, is itself sufficient. We do not need to witness the event to appreciate its significance. We do not need to be present when Gliese 710 crosses the threshold of the Oort Cloud to understand what that crossing will mean. The very fact that we can conceive of it, can model it, can feel something like wonder or unease or curiosity when we contemplate it, this is the remarkable thing. This is what separates a universe that merely happens from a universe that is experienced, reflected upon, understood. Consider what it took for us to reach this moment of understanding. The light from Gliese 710 has been travelling toward Earth for 64 years. By the time it reaches your eyes tonight, if you could see it, which you almost cannot without a telescope. That light left the star in the early 1960s, when humans were just beginning to venture into space, when the first satellites were circling overhead and the first cosmonauts were experiencing weightlessness for the first time. By the time that light arrives, it carries information about a star that has already moved slightly closer, has already continued its inexorable drift toward our neighbourhood of the galaxy. The photons that strike your retina are historical documents, records of a moment 64 years gone, and the star that emitted them is no longer quite where it appears to be. This is always true of starlight, of course. We see the universe not as it is but as it was, our view perpetually lagging behind reality by the time it takes light to cross the intervening void. But with Gliese 710, this fact takes on a particular poignancy, because we are watching a star in motion, a star whose position is changing in ways that matter to us, and every observation we make is already out of date by the time we record it. The astronomers who first identified Gliese 710 as an approaching visitor did so using measurements that were themselves the product of centuries of accumulated knowledge. They stood on the shoulders of Tycho Brahe and Johannes Kepler, of William Herschel and Friedrich Bessel, of all the careful observers who charted the stars and measured their positions and tracked their movements across the sky. They used instruments that would have seemed like magic to those earlier astronomers, space telescopes orbiting beyond the atmosphere, interferometers that combine the light from multiple observatories to achieve impossible precision, computers that can process millions of measurements and extract subtle patterns from the noise, The Gaia spacecraft, which provided the most precise measurements of Gliese 710's trajectory, is itself a marvel of engineering, a spinning observatory at the second Lagrange point that has catalogued the positions and motions of nearly 2 billion stars with accuracy measured in millionths of an arcsecond. This is precision beyond anything our ancestors could have imagined, precision that reveals the subtle drift of stars that appear fixed to the naked eye, precision that allows us to project their paths forward across geological spans of time. And yet, for all this precision, uncertainty remains. The trajectory of Gliese 710 is well established, but the detailed structure of the Oort Cloud is not. We have never directly observed a pristine Oort Cloud comet in its native habitat, have never sent a probe into that frozen realm to survey its inhabitants. Everything we know about the Oort Cloud is inferred from the comets that occasionally fall inward, from theoretical models of how the solar system formed, from analogies with other planetary systems that we observe from afar. The estimates of how many comets reside there, 1 trillion, perhaps 2 trillion, perhaps more, are educated guesses based on incomplete data. The distribution of those comets in space, their sizes and compositions, their orbital characteristics, all of this remains uncertain. When we predict that Gliese 710 will perturb approximately 100,000 comets into the inner solar system, we are making a calculation based on assumptions that future observations may revise. The actual number could be higher or lower. The timing could be different than we expect. The details are fuzzy even as the broad outlines are clear. This uncertainty is not a flaw in our science, but a feature of our relationship with the universe. We are finite beings trying to understand an infinite cosmos, and our understanding will always be incomplete. The goal is not to eliminate uncertainty, but to quantify it, to know how confident we can be in our predictions and where the gaps in our knowledge lie. The astronomers who study Gliese 710 are honest about what they know and what they don't know. They publish error bars along with their measurements, confidence intervals along with their predictions. They acknowledge that their models are approximations, that new data may require revisions, that science is a process of continual refinement rather than a collection of final truths. This humility is one of the great virtues of the scientific enterprise. It allows knowledge to grow, allows errors to be corrected, allows each generation to build on the work of those who came before. The comets themselves, those trillion frozen wanderers at the edge of the sun's dominion, are time capsules from the birth of the solar system. They formed 4.6 billion years ago in the swirling disk of gas and dust that surrounded the young sun, and they have remained essentially unchanged ever since. While the inner planets were being bombarded by asteroids, while oceans were forming and evaporating and forming again, while continents were drifting and mountains were rising, and life was evolving from simple chemistry to complex ecosystems, the comets of the Oort Cloud remained frozen and still, drifting through the darkness at temperatures barely above absolute zero. They are archives of the early solar system, preserving in their ices and their dust the chemical composition of the primordial nebula. When a comet falls into the inner solar system and begins to outgas, releasing the volatiles that have been locked in its ice for billions of years, it is revealing secrets about our origins, providing samples of ancient material that would otherwise be impossible to obtain. The comets that Gliese 710 will send toward us, arriving over the course of millions of years, will be messengers from the deep past, carrying information about where we came from and how our planetary system formed. This is one of the strange beauties of the coming encounter. It will connect us not just to the future but to the past. The comets that arrive will have been formed before the Earth existed, before the sun had fully ignited, before the disk of dust and gas had coalesced into the planets we know. They will carry water that has never been liquid, organic molecules that have never participated in biology, minerals that crystallized in conditions nothing like those found anywhere in the modern solar system. Each comet will be a window into a world that no longer exists, a fragment of a time before time as we measure it, before geology and history and life began their intertwined dance on the third planet from the sun. Scientists of that distant future, whoever or whatever they may be, will have opportunities to study these pristine samples, to analyze their composition, to compare them with the comets that arrived earlier, and look for variations that reveal something about the structure and history of the Oort Cloud. The disturbance caused by Gliese 710 will be, among other things, a scientific windfall, a natural experiment on a scale that no civilization could deliberately engineer, But let us not be too optimistic. The comets will also be projectiles, potential impactors, sources of genuine danger to any inhabited worlds that lie in their paths. The same icy bodies that carry scientific treasures also carry kinetic energy, and a comet striking a planet at tens of kilometers per second releases that energy in an instant, in an explosion that can vaporize rock and trigger global catastrophes. The comet that struck the Earth 66 million years ago and contributed to the extinction of the non-avian dinosaurs was probably only about 10 kilometers across, yet its impact released energy equivalent to billions of nuclear bombs, ignited wildfires across continents, filled the atmosphere with dust and debris that blocked sunlight for years, triggered acid rain that devastated ecosystems worldwide. A similar impact today would be an existential catastrophe for human civilization, even if it did not drive our species entirely to extinction. And the comets that Gliese 710 will send inward, while mostly small, will include some that are large enough to cause precisely this kind of disaster. The question is not whether dangerous comets will approach Earth in the aftermath of the stellar passage. They almost certainly will. But whether anyone will be watching for them. Whether anyone will have the technology to detect them early enough. Whether anyone will have the capability to deflect them before they strike. The million-year timescale is both a comfort and a challenge here. It is a comfort because it means that any dangers are far in the future, that we have time, unimaginable expanses of time, to develop the technologies and institutions we would need to address them. A civilization that has survived for 1 million years will presumably have solved problems far more difficult than deflecting incoming comets. It will have weathered ice ages and supervolcanoes, plagues and wars, resource depletion and environmental collapse. It will have faced challenges we cannot even imagine, challenges that will make the threat of cometary impact seem almost quaint by comparison. If such a civilization still exists, it will surely have the capability to protect itself. The comets will be a nuisance perhaps, a drain on resources, a recurring problem requiring ongoing attention, but not an existential threat. And yet the million-year timescale is also a challenge because it forces us to confront how little we know about the long-term trajectory of intelligence and civilization. 1 million years ago, our ancestors were Homo erectus, wielding simple stone tools and mastering fire, living in small groups on the African savanna and only beginning to spread across the old world. They had no writing, no cities, no technology beyond the most basic. If you had tried to explain to them that their descendants would one day fly to the moon, would map the human genome, would build machines capable of thought, they would not have understood you. The concepts would have been meaningless, the future utterly beyond their imagination. And we are in a similar position with respect to 1 million years hence. Whatever exists then, if anything does, will be as incomprehensible to us as we would be to Homo erectus. We cannot know whether it will be recognizably human, whether it will value the things we value, whether it will care about the Earth or the solar system, or the distant star approaching from the constellation Serpens. We are imagining a future that is genuinely unimaginable, and our speculations say more about us than about what will actually occur. Perhaps this is the deepest lesson of Gliese 710. It teaches us humility. It shows us a universe that will continue long after we are gone, that does not depend on our presence or our understanding, that follows its own laws and its own rhythms regardless of what we think or do. The star will arrive whether or not anyone is watching. The comets will be disturbed whether or not anyone is counting them. The impacts, if they occur, will reshape whatever worlds lie in their paths, whether or not anyone mourns or celebrates the changes. We are participants in a cosmic drama, but we are not the directors. We do not write the script. We merely play our part for the brief moment we occupy the stage, and then we yield our place to whatever comes next. But perhaps this humility is not a cause for despair. Perhaps it is instead a source of liberation. If the universe does not depend on us, then we are free to enjoy it, to explore it, to marvel at its wonders without feeling the burden of responsibility for its fate. We can study Gliese 710 not because we must, not because the survival of all that is good depends on our vigilance, but simply because it is interesting, because it rewards our curiosity, because the act of understanding is its own reward. We can contemplate the distant future not with anxiety but with wonder, not as a problem to be solved, but as a mystery to be appreciated. The star will come, and we cannot stop it. The comets will fall, and we may not be there to see them. But right now, in this moment, we can know these things, can hold them in our minds, can feel the strange vertigo of imagining time on cosmic scales. This is a privilege, not a burden. The night sky, seen from a dark location far from city lights, offers a hint of what future observers will witness when Gliese 710 draws near. On a clear night, you can see perhaps 2,000 or 3,000 stars with the naked eye, each one a sun like our own, each one potentially host to planets and moons and perhaps other forms of life. The Milky Way stretches overhead, a river of light composed of hundreds of billions of stars too faint and too distant to resolve individually. And if you know where to look, if you have a telescope and patience and a star chart to guide you, you can find Gliese 710 itself, a faint orange point among the countless other points, unremarkable in appearance, but remarkable in trajectory. It does not look like a star that is approaching. It looks like all the others, a static point in a static sky. But it is moving, drifting closer at a rate of a few arc seconds per century, gradually shifting its position relative to the background stars, creeping toward an encounter that is already written in the equations of celestial mechanics. That faint point of light is 60% as massive as the Sun. It burns hydrogen in its core at a leisurely pace, producing a fraction of the Sun's luminosity but doing so for a much longer time. Orange dwarfs like Gliese 710 have lifespans measured in tens of billions of years, far longer than the Sun's 10 billion, far longer than the current age of the universe. By the time Gliese 710 burns out and fades to a cold black dwarf, the universe will be unrecognizably different. The last generation of stars will have exhausted their fuel, and the cosmos will have entered the long dark age that awaits it in the far future. But that is speculation upon speculation, a future so distant that even the approach of this star seems imminent by comparison. For now, Gliese 710 burns steadily, as it has for billions of years, as it will for billions more. It is a patient star, an unhurried wanderer, a traveller that measures its journeys in millions of years and does not notice the microbes on a tiny planet debating its significance. There is a Japanese word, mono no aware, that describes the bittersweet awareness of impermanence, the gentle sadness that comes from knowing that all things must pass. It is the feeling you get when you watch cherry blossoms fall, when you see an old photograph of someone who is gone, when you contemplate the transience of beauty and life and love. And perhaps it applies here too to our contemplation of Gliese 710 and the cosmic future it represents. Everything we know and love will pass. The civilizations we build, the art we create, the relationships we cherish, all of it is temporary, a brief flowering in the vast emptiness of cosmic time. The star will outlast us, will outlast everything we have ever made, will continue its journey long after the Earth itself has been swallowed by the expanding sun. And yet, knowing this, we can still find meaning, can still feel wonder, can still experience beauty and connection and love. The impermanence does not negate the value. If anything, it enhances it, makes each moment more precious, each experience more vivid. We are here now, and that is enough. The comet that will one day fall inward, disturbed by Gliese 710's gravity, has been waiting at the edge of the solar system for 4.6 billion years. It was there when the first microbes appeared on Earth, when the first fish crawled onto land, when the first mammals emerged from the shadows of the dinosaurs, when the first humans looked up at the stars and wondered what they were. It has been patient beyond our capacity to imagine patience, frozen and still and silent. A time capsule from before there was time. And in another million years, perhaps 2 million, perhaps 5, it will finally move, will begin its long fall toward the sun, will grow a tail of gas and dust as it warms, will blaze across the sky of whatever world it approaches, will end its billions-year wait in a flash of ice and fire. That comet carries the same carbon and oxygen and hydrogen that make up our bodies, the same elements that form every living thing on Earth. It is our distant cousin, forged in the same crucible, separated by the accidents of orbital mechanics but united by the shared origin that connects all matter in the solar system. When we look at the night sky, we are looking at ourselves. The atoms in our bodies were forged in the cores of ancient stars, scattered across space by supernova explosions, gathered together by gravity into new stars and planets, and eventually into us. We are made of star stuff, as Carl Sagan famously said, and we are contemplating star stuff when we study Gliese 710 and its future approach. The boundary between observer and observed is not as clear as it might seem. We are not separate from the universe, we are part of it. A temporary arrangement of matter and energy that has somehow become aware of itself and its surroundings. The star approaching from Serpens is our neighbour, in a cosmic sense. The comets it will disturb are our relatives. The whole vast drama of stellar passages and orbital perturbations and comet showers is our story. Whether or not we are still here to witness its future chapters. And so, we arrive at the end, not of the story, for the story has no end, will continue as long as the universe persists, but of our contemplation. Gliese 710 is still out there, still moving toward us at 14 kilometers per second, still tracing its ancient path through the galaxy. In 129 million years, give or take a few tens of thousands, it will reach its closest approach, will pass through the outer reaches of the Oort Cloud, will leave its mark on 1 trillion frozen worldlets, will continue on its way as if nothing had happened. The comets it disturbs will drift inward over millions of years, some falling into the sun, some being ejected into interstellar space, some passing close enough to planets to pose a threat or provide a spectacle. Life on Earth, if it still exists, will continue in whatever form it has taken by then. Minds, if they still exist, will contemplate the encounter and draw their own lessons from it. What we know, here at the beginning, is that the encounter is coming. It is written in the positions and velocities of the stars, determined by the laws of physics, inevitable as gravity itself. We cannot change it. We can only understand it as deeply as our limited minds and instruments allow. And in that understanding we find something like peace. Not the peace of ignorance, not the peace of denial, but the peace of acceptance, of humility, of wonder. The universe is vast and ancient and indifferent, and we are small and brief and aware. The star approaches, the comets wait. And we, for this single shining moment in cosmic time, we are here to know it.